I'm Olivier Peltre. Yeah, thank you. Thank you for this invitation. So, the starting point of this work is an equivalence theorem between Bethe free energy, which is an approximation of the Gibbs free energy. So it comes from computational thermodynamics. And the fixed points of the belief propagation algorithm, which initially is a decoding algorithm. So the relationship between these two sides is a bit surprising and quite recent, although there is a long tradition in both sides. And so I will state this theorem at the end of my talk, but I realized that there was a natural homology theory that was connecting these two sides. Okay, so to start with, I would like to tell you what I understand by a statistical system and introduce the notations. So yes, so what I would like to call local statistics, it's the following data. So first you have you start with a set of microstates. So it should be like a topological space. It should have a measure, for example, Lebesgue measure or counting measure. Everything in this talk will be finite, so E will always be finite. And starting from the microstates, you get an algebra of observables. Take continuous observables, for example. And the dual of this algebra would describe measures. And inside measures, you have probability densities, so which I will denote by sigma. Okay? And so all these spaces live in some categories. And fundamental aspect of thermodynamics and statistics is the Gibbs state map. So it's a map that takes an observable, the Hamiltonian, to a probability density. So here the bracket denotes normalization. And so the fundamental problem we are concerned with is that this normalization factor, so Z, will diverge when E tends to infinity. So E will typically become infinite dimensional. So even when E is finite, you have a computational problem. So our point of view will be that we cannot perform any global observations. Okay? And so an attempt to overcome these obstacles will be to try to use the functoriality. And so in this table, if you move from one column to another, you always have a functor, okay? And so I will go quickly on this. But so by functoriality, I just mean that if you have a set map between the microstates, you have a pullback algebra morphisms between the observables, and then you have a push forward measure, and this push forward, which is a linear map, restricts to probability densities. Okay? And so what do I mean by a system? So, okay, the problem is that systems, they have a very large set of variables, but the interactions are short-ranged. And so that's what we will try to capture. At the same time, we are interested in collective phenomena. So the question is, if we can describe such phenomena. And so a system, for example, you have crystals. So a crystal has symmetries, but it's also very large. And then you have networks, you don't have symmetries, but variables are still short-range connected. Okay? And so notations, I will denote by omega the set of variables. IJK will be these like atoms or synapses, and we will cover omega by regions, okay? And I will denote those by alpha, beta, gamma, okay? And so the idea is that you will never observe anything on a region larger than your maximal regions, okay, which I will usually denote by alpha, okay? And I will use alphabetical order for this partial order of regions, okay? And when a region alpha contains a region beta, Well, the state of alpha determines that of beta, and so you have a projection from E alpha onto E beta. And so if we summarize this, we will think of X, this covering of omega by region, as a partial order, where it is a partial order. We will think of it as a category. And so microstates will turn this into a functor, okay? So we forget about this global E, and we'll only have local microstate spaces. And when alpha contains beta, you have a projection from E alpha to E beta. And these projections, induced by pullback, just algebra injections, okay? And so an observable on beta extends to an observable on alpha. It just does not depend on the variables in alpha, okay? Okay, so that's just the picture. And now I would like to show you these algebraic structures that appear when you consider these functors. Okay, so they are very natural, and they could be related to much more general constructions. So the first part, it's about combinatorics and incidence algebra. So I'll go quickly on this. It's very classical. Okay, and so just inclusion-exclusion principle. This formula is very fundamental. Okay, it relates. So I would like you to remember this one. It relates the Hamiltonian, which is written as a sum of potentials, and you have an inversion, okay? So here are these formulas. H, the Hamiltonian, is the sum of potentials, and you can invert this with just these coefficients, mu, alpha, beta. Mu is known as the Möbius function. You can do the same with the global total energy, H omega. You still have these integral coefficients, okay? And this is just related to this incidence algebra. So you have a ring and a convolution product. So this fundamental theorem of combinatorics is known as Möbius inversion, okay? So mu is the Möbius function, okay? So this is the more original part of my talk. So we introduced a chain complex of observables. So these spaces, they are just direct sums of observable spaces, okay? They're indexed by the nerve of X, which is a simplicial complex. So a zero simplex, a point is just a region. A one simplex is just an ordered pair, alpha containing beta. And so this formula for the boundary operator in degree 1 to 0, it's just like this. So you may think of it as a divergence. And on the right-hand side here, you have, okay, this, which I denote with a bracket, it just means that phi beta gamma, it's an observable on gamma, but you have to take the extension onto beta, okay? Okay, and so you have a homology theory associated to this boundary operator. You have a Gauss formula, okay? So by lambda alpha, you know, the cone under alpha, it's just all the set of regions that are contained in beta. And so you have this formula. If you sum a divergence, then it's just the boundary flux of this current phi, okay? So this allows you to compute the homology. And so it's a very simple result, okay? But what is important to remember, it's quite intuitive, is that the only homological invariant for these fields, so U alpha is just a collection of observables. Each U alpha is an observable on the region alpha. And under boundaries, the only invariant is the global Hamiltonian, okay? And so you could precise the result, okay? So the homology group is just the inductive limit of A, okay? That's very important, and it's acyclic. Okay. So by duality, you have also a chain complex. So D is just the adjoint of the boundary operator, but this acts on measures, okay? And here is the formula for the differential. So Q is a collection of measures, and this differential, dq alpha beta, it's a measure on beta. And so it's just Q beta minus this sigma beta alpha, which is just a notation, sorry, for the marginal projection, okay? So it's just you you integrate over the variables that are not in the region alpha. And this gives you a measure on beta. So this is a measure. And the cohomology is just the space of consistent measures. So if dq is 0, it means that q beta is the marginal of q alpha. Okay? And this can be understood as a projective limit. Okay? And so what I will call consistent statistical fields is just the subset, so consistent measures that are probability densities. And I will denote this subspace by gamma 0 of x. Okay? Okay. Yeah. And so, okay, this is the main problem. Okay, I would like. Okay, I think if you understand this slide, you will understand all the applications. Okay. So in thermodynamics, you are given a global Hamiltonian. It's a sum of interactions. And so the important fact is that along the whole homology class, this H omega is preserved. So you may change the H, with some U equal H plus divergence of phi, and you will preserve this global Hamiltonian. Okay. And so the problem is that if you try to think locally and take only local Hamiltonians, they don't account for interaction with the neighbors. And so the local Gibbs states, just defined this way, they are not consistent. The marginals do not agree. So the fundamental question we are addressing is, can we find a homologous U, so preserving the global Hamiltonian, such that the effective Hamiltonians, big U, define consistent Gibbs states, okay? Because a consistent statistical field is the concept we will use to replace the notion of a global probability density. We will not be able to observe global probability densities, but okay, a good criterion for these statistical fields is to be consistent. Okay. And so now I would like to address a few applications. So how much time do I have left?
8 minutes.
Oh, okay, perfect, yeah. Okay, good. Okay, so first of all, we have a Bethe free energy. Okay. So it's a local functional built to approximate the global Gibbs free energy. It was introduced by Bethe to study crystals. And so, okay, you start with local Gibbs free energies, okay? Say local because they are not taken on omega. So they are, okay, just defined usually with S alpha denoting Shannon entropy. And you would like to write each Gibbs free energy as a sum of free energy summons, okay? So you would like to do that because free energy is extensive. So you would like to think of the free energy of a large system as a sum of the free energies of its subsystems. However, the free energy is not linear, so it's not really a sum of smaller free energies. Okay, but you can always do that. So it's these equations are on functionals, but you can still do that. It's just a combinatorial problem. It's just Möbius inversion. And the Bethe approximation just consists to neglect this global summand, small f omega, and it's an extensivity argument. So you can prove that it's really negligible in some cases, but the one I know of uses the symmetry of the crystal. Okay, but that's the Bethe approximation. So I write f hat for this functional, and so it's given this way. So it's just combinatorics. So this is the Bethe free energy, and so the problem is to minimize this Bethe free energy. So P is a collection of probability densities indexed by the regions, and you would like this P to be consistent. And so this constraint, gamma 0, which is described by the differential, it means that dp equals 0, translates into Lagrange multipliers that are the right-hand side of this part. And you still have this zeta, which comes from these coefficients, so it's really a combinatoric thing here. Okay, so this is like the usual No, these usual theorems, variational theorems for defining the Gibbs state from the Gibbs free energy. Okay. Okay, so equivalently, just notations. If you let small u h plus boundary phi, and u like this, so this is the problem I showed you on the last slide. So if you have this u on this line, it is a critical point of the Bethe free energy. Okay. And now belief propagation. So it was a decoding algorithm originally, but it was discovered to only stabilize on critical points of this free energy. Okay. So here is how it is defined. So you will have beliefs that I denote by Q alpha. They are just positive functions or probability densities if you normalize. M are messages. They are indexed by pairs of regions, and these regions exchange information or whatever. And here now sigma just denotes a marginal projection as well. Okay. And so what I will do now is to introduce a couple operators and turn this algorithm into a transport equation. So this nonlinear functional, which I call nabla f. Okay, wait, sorry. So we start with this, effective energy. So yeah, it resembles a conditional Helmholtz free energy. And what I call this effective energy gradient is just the Hamiltonian minus the effective energy coming from another region. Okay? And the flux here, you see the effective energy here just of these regions that are not contained in beta but are inside alpha. So it's the effective energy of the outside but on beta. Okay? And so what we realized is that you can write this transport equation, okay? U dot is, so it's your collection of effective potentials, and they evolve you just add boundaries. And this boundary is defined, so this current, this flux is defined with these effective energy gradients. Okay, so this is just an ordinary differential equation, whereas the algorithm is really a discrete time algorithm. And so you have a vector field, and so this defines a dynamic over the collection A0 of x of observable fields. And so, so the important fact is that belief propagation is just a naive Euler scheme for this vector field. Okay? And actually it just takes dt equal 1. Okay. Okay. And so this homological picture also allows you to see these conserved quantities. So this is just the beginning of my talk. This is the homological invariant, the global Hamiltonian. And so this translates for belief propagation as a multiplicative invariant. Okay. And okay, so just to finish, just a picture of the equilibria. Okay, so this is the main theorem which I was mentioning at the beginning of my talk. The fixed points of BP are the critical points of the Bethe free energy. And so I don't really like this formulation because such a U, such that the Gibbs states are consistent, it doesn't mean that it comes from the algorithm. No, it's just in the homology class, but you don't know if you can obtain it from the algorithm. It may not be in the trajectory. So I would more like you to think of this this way. Okay, so you have this manifold, which is the collection of effectively consistent Hamiltonians. So nabla f equals 0. And this is the set of fixed points under BP. And you have an initial Hamiltonian here. The tangent space at 0 is just the kernel of D. And so you have these homology classes in green. But the big H does not evolve in a homology class. It's the small h. And so what you are looking for is this current phi, and u is h plus zeta d phi, okay? And so what happens is that zeta, so the image of the boundary is always transverse to this manifold, but because of this zeta, this sums, you may have singularities, okay? So this is a fact that is known numerically, but from a mathematical point of view, we don't know how to prove and to capture these singularities. Okay. And okay, now just to finish, just a few. So these are the first simulations I got for the algorithm. So X is just a triangle. You only have 3 variables, and the regions are just the segments. Okay. And you have the Ising model Hamiltonian. So this is BP, so dt equal 1. And this is, okay, it's just like mean values here that are depicted for different regions. And you see that they diverge very quickly because in JavaScript, like exponential of 2000 is already infinity. And so here I will keep the time interval constant, but you see that the Y scale gets smaller. You see it seems to explode and it seems to diverge, which changed a lot. But when you get dt smaller, so here it kind of stabilizes, but here is what happened for the continuous flow, okay? So yeah, it seems that the continuous equation in fact converges, okay? And so thank you. Yeah, I'll stop here.